Our whole world is pretty much built on concrete. We're talking bridges, dams, skyscrapers, these massive structures we rely on every single day. But they all have this hidden enemy, tiny little cracks that can grow into catastrophic failures. So how do you find them in time? Well, the answer, it's a bit more complicated than you'd expect.
I mean, it's a massive challenge, right? We're looking for flaws that are just millimeters wide on structures that are hundreds of meters long. For decades, the only way we could do this involved methods that were, well, they were slow, they were expensive, and yeah, you guessed it, incredibly risky. So before we jump into the really cool high-tech stuff, we got to take a look at how things used to be done. And let's just say the old system was, well, it was full of its own cracks. So the traditional way? You had inspectors, actual people, who had to physically check out these massive surfaces. I'm talking dangerous work, like hanging off the side of a bridge or a dam. And on top of that, it was so slow. Plus, it's totally subjective, right? What one person calls a minor issue, another might see as a huge critical flaw. That's why automation, using things like drones, isn't just a nice little upgrade. It's an absolute necessity for keeping things safe and reliable. Okay, so this is where it gets really interesting. This is where modern AI steps onto the scene. Instead of sending a person up there, we can just send a camera and teach a machine to have an eye for detail that's, frankly, better than human. And the secret sauce here? It's a concept that's actually inspired by our very own brains. All right, the specific tool we're talking about is called a convolutional neural network, or a CNN for short. The easiest way to think about it is like an artificial brain's visual center. We don't sit there and program it with a bunch of rules like a crack is a dark line. No, instead, we just show it thousands and thousands of pictures and let it figure out the patterns all on its own. So how do you train it? The process itself is actually pretty straightforward. Researchers grabbed this massive data set, we're talking 40,000 images, and they went through every single one, labeling them crack or no crack. Then they just fed all of that into the CNN. The model just chews through all that data, learning all the super subtle details, textures, lines, shadows that tell you this is a dangerous crack versus that's just a harmless mark. But, and there's always a but, right? They quickly found out it wasn't quite that simple. I mean, the AI got pretty good, but it had this hidden weakness, a problem that honestly messes with almost all computer vision projects. The real world is just messy.
So here's the deal. The AI is basically trying to read the concrete, right? But the pictures it's looking at are filled with all this visual static, what we call noise. And all that noise just confuses the model. It ends up either missing real cracks or, crying wolf over nothing. And you know what's kind of surprising? It's what actually counts as noise. It's not just like digital glitches. We're talking about the natural, rough texture of the concrete itself. Or shadows. Shadows can look exactly like a crack. Then you've got blur from a moving camera, or even just the artifacts from saving the image file. All of this stuff basically smudges up the AI's glasses. So if the problem is just a pair of smudged glasses, the solution is kind of obvious, isn't it? You clean them. And that is exactly what the researchers realized they needed to do. So they brought in a brand new first step, image denoising. The idea is, before the main crack-spotting AI even gets a look at the picture, another, totally separate algorithm goes in and does a digital cleanup. It's smart about it, too. It gets rid of the shadows, the blur, all those artifacts, but it's super careful to leave the important stuff, like the sharp edges of a real crack, completely untouched. It's just such a simple, elegant idea, By cleaning the smudged glasses before the AI tries to read, you give it this crystal clear picture to work with. And that one little change, it had a huge impact on how well it worked. Okay, so how much better did it actually get? Well, the results are, honestly, they're staggering. Okay, get this. On average, just by adding that one denoising step, the AI models they tested got a 13 to 15% boost in their performance score. Now, for those of you who follow AI, you know that's not just a small bump. That is a massive leap forward. All right, let's look at a specific case here. There's this powerful AI model called ResNet 101. It was already doing pretty well, scoring around 84.6%. But after they started cleaning its images first, its performance shot up to over 96%. Think about that. It went from being a solid B student to a straight A superstar, all because it cleaned up its data. But look, getting the highest score possible is fantastic. But in the real world, it's not just about accuracy, right?
You've also got to think about efficiency. How fast is it? What kind of computer does it need? Can you run this thing on a little drone, or do you need a monster supercomputer back at headquarters? And this is where the research is so cool. It gives us options. So on one hand, you've got the heavyweight champion, a model called Xception. This thing delivers the absolute best accuracy, but it's big, it's a bit slower, it's perfect for when you send the data back to a big server for analysis. But then, on the other hand, you have a lightweight contender like ShuffleNet. It's wicked fast and tiny, which makes it absolutely perfect for running right there on an inspector's tablet or even on the drone itself out in the field. So you see, it's two different tools for two very different jobs.
So let's bring this back. What does all this actually mean for the bridges we drive across every day, or the buildings we live and work in?
Really, it all boils down to one crucial point. This isn't just a story about a fancy new AI. It's a story about preparation. The real breakthrough here wasn't some super complex new algorithm. It was just a smarter process. By simply taking the time to clean the data first, they made the AI that much more effective.
And the real-world impact of that, it's huge. We're talking about safer infrastructure because we can spot these tiny problems way, way earlier. We're talking about inspections that take just hours instead of weeks. Ultimately, this moves us towards a future where we're not just reacting to failures after they happen. We're proactively managing our structures so they never become a crisis in the first place.
And that really makes you wonder, doesn't it? What's next? If we can do this for concrete, what other invisible dangers could this same approach help us see? Think about it. Microscopic metal fatigue in an airplane's wing, or hidden water damage inside a wall. What other critical flaws could we find before they ever have a chance to become a disaster?